So another way of showing change, looking here at migration patterns. This here, this state of interest is Iowa, and we're looking at people that move to Iowa and people that move from Iowa, where they move to and from. So if we're looking at Iowa welcomes, we see arrows connecting the states. So the green state here being California, going to Iowa, and the people that are the largest group of numbers that are moving to Iowa are, not surprisingly, the neighboring states and California. Now, where people from Iowa are moving to, again, not surprising, the neighboring states, but this time Texas they're moving to as being the highest value. So these are two sets of micromaps side by side, and what we're showing is the flow into Iowa. Again, now light green showing the cumulative states that have already appeared. Seeing the light green flow, the flow into Iowa in this column, and the flow out of Iowa in this column. And so you get to see these little edges connecting the states, so that it's a little easier to emphasize that we're looking at the change from Iowa to the other states. And it's of interest to see how different these are from one another. Already the difference we noticed between Texas and California, also Florida there. So that's showing some flow. So that again showing change, and that's a very common graphic. Very famous set of historical graphics are by Charles Joseph Minard, and these are flow maps. And you'll see lots of these more modern ones. This particular flow map, we're looking at a world map, and Minard is looking at flows of wine from France to various other countries. And so we're coming out of France and flowing into other countries, and the width of this band is proportional to the volume of the flow. So you can see that very little going into Canada in this time. This is 1864. More going into the United States. I'm not sure that's 10 times more, but maybe it is a little more than that. And some going into the Caribbean, probably more in the French colonies, and then into South America, and again into Algeria as a French colony, and then with its European neighbors. So that's interesting, seeing the flow and how there's very little moving in the Indian, China, Australia, and so on. Where this one's going, I don't know. Antarctica. Not sure where that's going. This is probably the most famous of Minard's maps, and this is the Napoleon's March on Moscow, perhaps the most famous anti-war map. Minard used these flow maps to show the colossal waste of lives in war. He also did one from Hannibal. And what's interesting for us is the number of dimensions that have been added to this. There's a huge amount of data that's presented in this map. I think it's in all data sets, as I said many times, are interesting. There's no data set that really isn't interesting. And they're best if you get the background. So I would suggest you go and look at, I put up some videos here on my YouTube channel where we're finding this thing, showing about the background of Napoleon's march to retreat from Moscow. But let's look at an English version of this one. So we're looking at the losses over time. So what we have here is the entrance into Russia. This is the Grand Army of Napoleon. It's over 400,000 men. And we're moving from west to east, marching on Moscow. And as we move from west to east, there's some sort of diversion, some fraction will go off for some reason, to perhaps skirmishing, perhaps for some other reason, off of the general trend, and then come back. And we're moving from west to east along this gray line. And you see that unlike Minard's French wine, this flow is actually diminishing. This flow is getting smaller as we're moving west to east, and that's because these men are dying. The Grand Army is being killed off either by violence or by other means. And you can see wherever there's a little edge here that there's some big change. So we start off with over 400,000 men, and by the time Moscow is taken, there's only 100,000 people left in the Grand Army. And then there's the retreat. So the Russians just evacuate from Moscow, and they don't get a surrender. They just completely ignore Napoleon and the Grand Army. So they eventually leave and come back, and they're coming back, and you see even more so, more and more people are dying, and it's getting very tiny. Only 24,000 of the people that made it to Moscow, 24,000 of the 100,000 are alive at this time. And you see when they cross rivers, it'll be an abrupt change. This one's joined from that other group there, so they're back up to 50,000. Cross this river, huge losses. We're going from 50,000 down to 28,000. And ultimately, there's about, with this group of 6,000 coming back here, but right here, there's only 4,000 people. The 6,000 out of the 22,000 come back here, gets to 10,000. Enormous losses. So you've got these dimensions of the spatial location, X and Y, the size of the army. You've got some sense of time, although it's not, is it marked there? It's not exactly marked there. It is marked on the way back, though, on the return journey. We actually have on this bottom graph here the date, so October 18th, 24th, so time increasing from right to left here, following the journey back, with each point, significant points here at this river, what the date was, and also what the temperature is. So this line here, that's 0 degrees Celsius, that's freezing. And minus 12 degrees, minus 25 degrees Celsius, minus, another 12, I guess, probably 37 degrees Celsius, down to minus 40, minus 38 here. So terrible, terrible conditions, and you can see that this corresponds. So you've got now, at least in the return, you've got some more dimensions of the date and the temperature, and that corresponds to that. So a huge number of dimensions being displayed. And a tragic story. You can't imagine why the Germans in the Second World War would want to advance on Moscow, advance on Russia, knowing the Russian tactics of just withdrawing and destroying all of the crops, etc., so the army can't survive. Anyway, if seeing that map would deter you from following the same strategy. So here's another way, perhaps the simplest way of adding dimensionality. So we have the locations. These are locations of people that are producing sods. This is a map of Arkansas, so you can see the various, I'm not sure, I assume counties inside Arkansas. And these are locations of people that produce sod. This is for a turf grass study. And the size of the circle is, the area is proportional to the number of sod producers at that point. And presumably some redundant encoding here of the color, but to just check that, you should go to this URL and see what that color is. That is sometimes called a bubble plot. I don't know why we have to add names to these things, but just encoding the magnitude of this third variable as the area of this, at least now, nice and regular regular geometric shape. Okay, so that's something called a bubble plot. You'll see that lots of times, like in modern things here, Google Earth, you'll find bubble plots here. So we're looking at, again, the size of the circle and the redundant encoding with color going from green to dark red, showing the magnitude of what we have in these various locations here. This is looks like border between Belgium and the Netherlands. And it says zinc, but I can't recall. I wish I'd written down what that was that I picked up there. Imagine that it's concentrations of this particular metal, perhaps in the land. Anyway, so it's following the border there, which seems to be water. So bubble plots, you'll see them all over the place. Again, I'm not sure it's worth a name, but it's sometimes called that. Well, like everything else, there is a problem with using encoding magnitude by area, particularly bubble plots where you are having bubbles appearing side by side. The redundant encoding is helping get away from this, but if when the actual area that you perceive for that circle depends on what's around it. So this is an example that these two middle circles are in fact the identical size, and clearly the one on the right looks a little smaller than the one on the left. That's entirely our visual system doing that, increasing that contrast in size so that we can detect that this one is much bigger than those around it. This is much smaller than those around it. It's almost like our system exaggerates that effect. So these are all examples of glyphs. We've seen glyph is a notion of that it's just some mark that encodes a lot of information. Here's a classic glyph from the Mayan calendar. This is day 10 of the calendar, encoded as a particular ideograph. It's just a picture and encodes a lot of information. So it's just a mark that allows us to encode a bunch of information. So we're going to think about glyphs more generally, and again look to maps for how you might use glyphs and how they've been used in the past to encode more information. So one of the earliest use of glyphs is by Francis Galton, who we've seen before when we talked about quantile plots. Famous 19th century statistician, Francis Galton was one of the first persons to actually produce weather maps. And what we're looking at here is northwestern Europe. You can barely see there's Ireland there, and there's the UK, Scotland up here, and the coast of France, the top of Spain here, and the Mediterranean here. So you can just see in Norway, it's in Sweden. So what we have is a grid here, and he's taken data that's been reported, and we're looking at encoding the value. In this particular case, looking at barometric pressure. Barometric pressure measured in inches of mercury here, of a column of mercury. And what we have is that, let's see, the highest pressure, 30.71 above, is going to be in red, so that's kind of high pressure, and then in black will be lower pressure, and the zero is going to be sort of the empty circle, and the extremes will be more ink. So this is going to be black, so this is a fairly low pressure, and the highest pressure here is the red with the most ink on it, so high pressure down here. So now you get to see patterns of kind of high pressure with a bounder here with the switching over to the lower pressure, and much lower up here over Norway, bottom of Norway and Sweden. If I've got that right. I believe so. So the ink density is giving you some sense of the magnitude with some origin in the middle here between red and black. The origin being distinguished by the two different hues. Okay. Another thing we might learn from maps are level curves. So if you've had any experience with topographic maps, if you've been hiking or canoeing, etc., you've been accustomed to topographic maps. This is showing the height of, these are level contours, so these are 130 along here. All that's here is that, I should check this, I assume that's meters, 120 meters, that contour that's going along there, 130. And so as it goes up, it's 190. Here's the highest, so that's where the peak is. And then 180, 170, 160, or something 150, a little dip here. And where you see points, lines that are close together, that's rising rapidly from 110 up to 190. So that's a much more significant climb if you're walking from here to here than to try to walk up from there, where it's a much slower change. So topographic maps are a way of showing the third variable here coming out of the screen, the height of this volcano on New Zealand. Okay. And so that can be used not just for something physical, but also in weather maps. People use that for this more abstract notion that we've got the barometric pressure. So again, we're looking at level curves here that have the same barometric pressure here. So these are, they're called isobars, isobarometric, right? They're the same barometer reading. And looking at level curves of barometric pressure. And this is for a hurricane. And so we don't have very many hurricanes heading to us. We're up here, they're the Great Lakes, Lake Michigan, Huron, Erie, and Ontario. This is the 1954 Hurricane Hazel that actually reached Toronto, which is a rare occurrence. And so looking at the isobars, we can see this low pressure system here where the hurricane is, and increasing high pressure away from it. And that low pressure system that's moving up. And when it actually hits Toronto, you can see again the isobars here of the low pressure system being concentrated right above Lake Ontario. So that's a hurricane in our neck of the woods a very, very long time ago. You also see these at, weather folks use these at continental levels, so the entire North American continent here, and looking at isobars, see where there are, and then marking them with low. So here's the low L, H, high pressure, and you start to see boundaries of where it's switching between high and low pressure, where there's a low pressure ridge moving along. And by looking at these patterns, begin to think about how is this affecting weather. Low pressure is often associated with precipitation, with rain, and high pressure with clearer skies, etc. So we begin to look at these pressure readings and make weather predictions from them. But again, it's just like that topographic map. So you're climbing up this hill of high pressure, down into this valley of low pressure, up the hill to the high pressure. So the level curves are telling you what this three-dimensional surface of pressure looks like. So we're getting that third dimension with the level curves. So this goes back again to Galton. And Galton, here we're looking entirely at the UK. So again, Scotland and England and Wales down here, Ireland on the west coast here. And now we have glyphs that are rather complicated. And these glyphs have got a lot of information. So they have the spatial location of where is that, what part of the country is that located on. But then it's got encoded a lot more information. This little U that we see here is actually wind direction. So the wind direction, the wind is blowing in that direction from southeast to northwest at that point. From here, from southwest to northeast, the wind's blowing in that direction. The greater the ink associated with it, the greater the strength of the wind. You see down here in the scale at the bottom. So the orientation is the direction of the wind, and again, the more ink, there's a gale that's strong, and the circle is calm. So on top of that, we have as well some encoding of precipitation. And so the precipitation, again, is shown here with circles with rain and snow. I don't think we see any snow here, do we? No. And but there are places where there rain, all these circles. And then what we have here is the cloud level. So this down here where you see these dots are mostly clear blue sky. This presumably is entirely clear and calm. And the more ink there is, the more cloud cover, which is why when it's raining, it's completely covered with circles. So you get a lot of information. You've got spatial location, that's 2 dimensions. You've got direction of the wind, that's another 2. You've got the strength of the wind, that's now up to 5. The cloud cover, that's 6. And then whether it's raining or precipitation or not, that's 7. So 7-dimensional data, 7 dimensions encoded on a 2-dimensional display. That's pretty impressive. So a lot of this stuff is from maps and really from weather. People have been using a lot of this stuff long before we ever used them in data analysis. In fact, they really go to town here. So if you look at how complex this map can be, I'm going to see if I can zoom. Whoops. I'm going to see if I can zoom in here. Yeah. So we look at this map, and maybe I'll recognize Florida down here, so you can see that we're still talking about North America. There's Newfoundland on the east coast, Nova Scotia, east coast of the U.S., and the Gulf of Mexico here. And so what we have is we have these level curves, those isobars, and we also have these sticks everywhere, these like little hockey sticks. And what these are they're pointing in the direction of the wind is blowing, and then the number of little flags that are off the end of them is proportional to the strength of the wind. So up here you can see some very strong winds with these sticks that have lots and lots of little flags off them, very strong winds. And finally, you also have the temperature. So the temperature is in degrees Celsius, it looks like, from 26 on the hot end down to minus 30 on the low end. And you see the colors being used up here. So up here in the Arctic, you're getting as low as minus 10 degrees Celsius. And down here in the south around Mexico, you're getting high 22, 24 degrees Celsius. So a lot of information on top of that two-dimensional display. So, well, we can add information on maps in R, and it's important to realize that there's a whole library of maps, and there's lots of ways to get maps we'll talk about in a bit. And so I can get these maps. I can go and get the map of Canada. I've got some precipitation data here that's available on the course website, and we'll look at plotting these cities on the map. And I'm just going to take a subset of the cities here, these particular indices here. And my data frame has got precipitation, latitude, longitude, and population. So if I look at those, I put those cities on a map, and then I want to plot, so I can plot the map of Canada, just for looking up in this map database, this world database, Canada, plotting it, not filling it, and then putting on some symbols now at the city locations, at the longitude and latitude. That's the longitude is going to be X and latitude the Y. And what we're going to put on are thermometers. These thermometers are going to show the proportion of precipitation. You know, the precipitation is measured in millimeters, and I'm just going to divide by a fairly large number, 2,000, and show that in red. So when we add that, we get a map like this. Now this map is for precipitation is really good. And why is it good? Well, we have the spatial location here, and we're not looking at area or anything else. We're looking at the length of the bar, making these comparisons. So it's very easy to see that these where there's a lot of precipitation here on the west coast in Vancouver, on the east coast in St. John's, Newfoundland, and not so much in the prairie provinces here in the middle. And the advantage of this thermometer is, as we've noted in the past, if I can compare, if it's easier, if the relative difference is, again, following Weber's law here, if the relative difference in the dark part is huge, that makes that easy to tell apart. If that relative difference is not so large, it may be easier to tell, you know, Vancouver from St. John's here by the white part. So having that little extra frame there makes it a lot easier to tell which of these has greater precipitation, or between these two, which has greater precipitation. It's easier to tell the red parts here than it is to tell the white parts. So we've seen that before, and that's again an application of Weber's law. Here's another statistical glyph. I think by far what I think is the best statistical glyph representing the electoral college votes in the United States for the most recent presidential election. And so you look at the states here now in the background. That's how their electoral college went. Pink now for the Republicans here and red for the Republicans in the pie charts. But the pie charts themselves now are actually showing the proportion of votes that went for each of the parties. So in California, for example, all of these votes would go blue for Clinton because the Democratic Party won a lot of the votes. But clearly, there's a significant fraction that is not that have voted Republican, and some that voted for others like Gary Johnson and other candidates. In the same token, let's see the other way. Here's one, Texas, that went for that goes entirely for Republicans, where Trump has more than half of the proportional vote, but there's a significant chunk that is voting Democrat, but the entire electoral college goes that way. So it's easy to see, especially when there's predominantly just two candidates in an American election. And pie charts are fantastic for seeing whether or not it's close to 1/2 or not. You see how close it is in Florida here with Clinton clearly getting less than half, much more or less than half than Trump. And you can see how close these races were up here that went to the Republicans, where Clinton has effectively lost the election in these very close races. The other thing is that the size now of the circle is proportional to the number of electoral college votes. So you can see that how important these big states are, or in determining the outcome of the election. Even though they're mixed, they still go all one way or the other. So it's an interesting way to determine the leader of the country. And so I think the intention here is that to balance off the proportion of the vote with the geographic location. Okay, so your proportional size of the vote, but also the geography, so that states, you go state by state. So the states are actually the ones that are voting. They're the electors in the states. And the popular vote is just determining, informing those electors how they should be voting. So looking at statistical glyphs as well, I looked at, you can put any sort of glyph on a map, and here's a historical map taken from paper here by Michael Friendly, which shows eikosograms on the French map, again talking about the distribution of passengers and goods throughout France, and just placing again a statistical graphic on the spatial map, just like we had with the pie charts or with the thermometer plots. You want to be able to put any kind of statistical graphic, any glyph. These are all different glyphs showing, so you can see the spatial relationships here. In fact, that glyph can be any statistical object, and here's something that I've taken from a paper by Wickham, Hoffman, Wickham, and Cook in environmetrics, and this was a data set that was part of a competition. We're looking at remotely sensed temperatures over Central America. So you can see underneath here the gray, that's the bottom half of the United States. There's Florida, that's Mexico, the Yucatan, down here Panama, and South America, the bottom right corner here in the islands. And what we have here are looking at grids, and every one of these grids is the same size, and what's displayed on that grid now is a time series of temperature. And so we can see we place a time series at every point here, and this is the time series of the residuals after removing some seasonality from the time series themselves. These are remotely sensed time series. That's why we have them across this entire grid. And you can just see the differences now in those residuals after the seasonality is removed. Low values here compared to what's over the southern U.S. Here there's much more variation. And again, when you hit the land masses here over the South America, you see quite a big difference between landmass and the water. And what's of particular interest is noticing this spike in the water over here, this sudden rise up here, and this is the El Nino, very warm temperatures in a particular time. This is over 6 years, 1995 to 2000. So in that time period, 1 or 2 years, there's a big spike in temperature. And that's sometimes called El Nino, that the water is much warmer, and that has an effect on weather patterns. And you could have anything, again, any graphic here. So on these grids, there are other data here, high cloud versus surface temperature patterns. So in fact, every grid here is a scatter plot. And if the scatter plot, then instead of having the whole scatter plot here, we may be interested in just the smooth behavior. So add a smooth. These are the low S smooths that you can see changes. So you can see different patterns that are spatially located, that are peculiar to the geography. So that, again, the glyph can be anything, and so it can be very rich, contain a lot of statistical information. These are all of the low S's on top of each other, so you get some sense of the variation in the low S curves over the whole map. What we have produced here, student Jawa Liu and myself, is this package called Glyphs. It's not yet on CRAN, but it's available on the course website. It needs to be a little cleaned up a bit to be on CRAN, but you can install it as a package. And the interesting thing about the Glyphs package is that it at least has a possibility of making any glyph. So I want to take a list of data sets that I'm going to apply something to. This is the cities that we have in Canada here. I'm looking at the Canadian cities, and then looking at producing a bar plot for each city, where the bars are beside each other, there's no axis. Use rainbow colors, and I'm going to use the data there is going to contain the number of days of precipitation, the precipitation in millimeters, and the population of the city. So a bar chart of 3 items. So once I make those glyphs, so I will have these list of glyphs, and then I can plot them. So I find out where everything is on the map that I'm interested in, the Canadian map. That's just getting me the ranges so that I can have my X limbs and Y limbs be the proper. And we're using the base graphics, but you could use grid graphics with these glyphs as well. So plot glyphs, where location, and just give the glyphs and the size of the glyph in the coordinates of the map itself, and then plot the glyphs, and then just add the Canadian map of Canada on top. We get something like this. So now you see bar chart. The automatically has, you can choose this, but it's got some alpha transparency. So it was number of days of precipitation. Then the green is the precipitation in millimeters, and then the blue is the population. So you can see the huge population down here in Toronto, largest population of this group here, very small in St. John's. And, I'm guessing that's Halifax, Montreal. And where it's wettest, the number of days and precipitation. The number of days here is definitely largest in Newfoundland, even larger than Vancouver. But the precipitation is about the same. Notice we don't, unlike that temperature thing, it'd be nice if we put that entirely in a box, so that we'd have some sense of how different is this green bar from that green bar. It's very hard to tell without that box. Again, Weber's law being the applicable thing there. So, Galton again. So, back to Galton again. Galton did a ton of things in this book back in 1863, looking at weather patterns and weather data. And one thing that he did was looking at morning, afternoon, and evening, right? So morning, afternoon, and evening, looking at the barometric pressure, the wind and rain, and the temperature data. And so just seeing quickly, but this is what a fellow named Tufte calls at something called small multiples, just to draw attention. If you've got small multiples of the same kind of thing, you can sometimes see patterns as they change, as you're looking over those small multiples. Which ones look alike, which ones look different, how do they differ? You know, so here we're looking over time, and this is the symbols that he's using. And the map that he's got here, we're looking at all of Europe here, with the exception of Spain at the bottom of Italy. We're looking at Western Europe map. And so he produces a few pages of this stuff day by day. So each 3x3 grid is a day. So you can see things changing over time. Having enough multiples of things over in one display, you can get a sense of how things change. Okay. Here's an interesting application of that idea of small multiples. And the application here is, again, the temperature data that we had before. Let me just zoom in here so you can see that we've again got the bottom of the US and Mexico and the top of South America. And what we've done is we've arranged these things so that they are months, January, February, March, April, down to December, and then 96, 97 arranged as rows. So each row is a year, each column is a month. And there's a simple model fitted to the temperature data that, you know, removing months and years, the averages for each of those, and then these are the residuals. And so the residuals from those models are colored for every one of those grid locations that we had before, and you're getting on a color scale here, the darker it is in red, the larger, more positive the residual is, and that is, I guess, it's hotter than the model would suggest, warmer, and the blue is it's lower temperature than the norm. And again, it's not hard to see now the El Nino effect of that red temperature appearing just off the coast of South America. Okay. Very, very cool application of small multiples, model fitting, right? Looking at residuals. And every one of these little grid parts is a square replaced by a single glyph. So there's a lot happening here, but tells a story. So it's just about being very smart about laying out this information. Any questions about this? No? All right, let's go back to micromaps. This is another way of showing change and with small multiples. So here, they're looking at rates over time, unemployment rates, and the years 2000, there are 4 years being shown here. And looking at the high unemployment rates are in red, the low are in blue, and the middle, 60% roughly, are in gray. So in any year, you can see where there's large unemployment in the red and where there's low unemployment in the blue. What's below is between the years, we're just showing which states actually changed color and what new color did they go to. Right? So California went from gray to red, so we're marking it as red there. Right? Up here, Michigan went from gray to red. What is this? Minnesota, I'm guessing. Yes, Minnesota went from blue to gray, so the gray there. So you can see the changes between years. Which state did the change happen? And this is identified by the color here. So this is a response, if you will. The color here with roughly the bottom 20%, top 20%, in the middle 60% chosen. The odd thing here is this little bit that's sticking out. That little bit that's sticking out is anything that's sort of beyond the fence in a box plot. So these are where the outliers are, this little tiny thing. Okay? And it's not necessarily on the same scale. All right? So a nice way of just showing the change here, again, entirely, all these micromaps are doing are identifying which are red, which are blue, and not so much the magnitude over the whole country. Here's another modeling exercise. This modeling exercise, these are called conditional choropleth maps. They're choropleth maps that are showing colors by region here. Inside, we're looking at a much smaller than the states, a much smaller aggregation level. And we're looking at the aggregation level are these health service areas. We're looking at white males, 65 to 74, from 1988 1992, and the lung cancer mortality and deaths per 100,000. Okay, so roughly divided into thirds. The blue are the low values. The red are the high values where there's lots of mortality. So we see the red concentrated down here in the Mississippi Valley, the blue a little more up in the north here. And we've got 9 different micromaps here. And the 9 different micromaps are because we divided these into 3 columns according to this variate. And this variate at the bottom here is a slider that has annual precipitation. So the annual precipitation in inches, so low precipitation of rain, so rain or snow, medium precipitation, middle 38%, top 40% here. So these are not evenly placed. There's at particular locations. And they're at locations where we're trying to separate all the regions that have precipitation between 3.05 and 29 inches of precipitation appear in this column. All the regions that have between 29 and 44.9 appear in this column. Those between 44.9 and higher appear in this column. Okay? Actually, it's greater than 44.9. In the rows, similarly, correspond to percent below poverty level. So the higher the percent below poverty level, the more poverty there is, that's on the top end up here. So the top row is high poverty, bottom is low poverty. Okay? And again, these things are chosen. There's 27% here, 56% there, 17% there. And now we're dividing and saying, I've got 2 variates now. I've got a model. I've got a response, the lung cancer up here, right? The lung cancer rate. And I've got 2 different categorical variates. I've got the annual precipitation into 3 groups. I've got the percent below poverty level in 3 groups. So I can think about a regression style model of this lung cancer on these different regions. Okay? So I can get a fit. If I can get a fit, I can measure how well it's doing. So now it looks like the red is really concentrated up here where there's lots of poverty and curiously lots of precipitation. Right? So what's the relationship between this variate and the others? So that's called a CCmap or conditional choropleth map. You can get these static versions in the map tools package called CCMaps. You could build your own interactive one if you want to build one with our Shiny. That might be an interesting exercise. So you can build a web-based one. Or you can build one with some code I'll put on the website using loon in a function called CCMaps loon. And that would produce something like this. And this one actually happens to be looking at Columbus, Ohio, and residential burglaries and vehicle thefts. So we've got crime up here, high crime, low crime, median crime, and producing by the housing values and plumbing. I can't remember what plumbing is here, what that's a measure of. And we have these sliders so we can see whether or not as you move these things around, you're redefining the categorical variate. And you'd like to redefine these things. Can you find cutoffs? So it's kind of a little different than a regression. Can I find cutoffs that are going to allow me to separate the red from the blue from the gray values? Right? And in any one of those, when I do that, there'll be an average value of this response for all of the geographic regions in that cell, right? And therefore I can talk about how well that fits the actual data. I can get the equivalent of an R squared. So my R squared down here is 0.41. And I can start to move sliders around. Can I improve that R squared? Doesn't look like very well. 3.7, 0.48. You start moving these guys around. So the conditional choropleth maps are, you can also get a Java version from Dan Carr's website. But this is going to be a loon, so you can zoom in and do everything else like before, and have it linked to scatterplots, etc. So I guess we'll end there. So until next time.
Okay, there are a lot of ways to get maps into R, and I'm just going to show you a couple of them. There are, in fact, more ways than I'm going to show you here. But some ways there's a library that has maps in it. In the library, you can get a map of various countries in the world. Here we'll pick up the map of Canada from this library of the world. We could also use it from the map data package, which provides another database, World Hires, that is also has a map of Canada. And you can see we're just picking up the X and Y limbs to figure out how to plot that. So the two maps, you see on the left is the maps of Canada from the World Database, and on the right the same map from the World Hires. It has got a little more detail, such as these Great Lakes that appear in Canada. So they're slightly different, but either one will do for a map of Canada for most purposes. Map Tools also has looking at other ways of getting map data. So here, for example, I'm going to extract data from an URL, an HTML file. And there you'll find that download a shapefile. And these shapefiles end with .shp. And you can read the shapefile just from reading shape spatial. And here we're going to get rows of local data. So these are Kitchener-Waterloo roads, and another shapefile with vegetation, and then also where there are bodies of water, and finally where there are water lines. So when we have all of these, we can plot these. So there's a special plot method for every one of these shapefiles. So we plot the KW roads, and then add to that the vegetation, add to that the water bodies, and add to that the water lines, giving some slight alpha blending there. And you get a map that looks like that. The KW region with the roads on in gray, the vegetation in green, the water bodies in blue, and the water lines in red. So that's nice. There's all kinds of maps like that available from a variety of municipal sources and national sources and international sources that you want to be able to grab as need be. Maps that are built like that from shapefiles are easily added to Loon. So here we're looking at Loon, and you just get a plot in Loon, and then you find the roads layer. You just layer that shapefile, KW roads, on top of the plot, scale it, and layer each one of these maps on top. And we'll get a map that is interactive. And we can choose to hide some of the layers or show them again programmatically or through interacting with the Loon inspector. So that would look like this. And you see that's in the inspector. You can see that the different layers. So I can turn off the water lines or the vegetation and bring them back on just by bringing the vegetation back and the water lines back. So that's Loon. Of course, being Loon, we can zoom in just with scrolling and see the different parts. We can move this around, and just pan one way or the other, etc. And again, just get back to the plot of the whole map there. That's very handy because we could have a scatter plot on top of that with in Loon with various sorts of plot symbols, including images. So that's what it looked like in Loon. Google Maps is, of course, a nice place for source of maps. These will come across. Here is this giant map with a lot of detail. Here I've just picked up the longitude and latitude, which is near the University of Waterloo, and the map type that I want, and the how zoomed in I would like to have this. And then to plot, I just do ggmap of the map. I get that figure, which I can add to, etc. I can add things with it's like a ggplot2, so I can just get some data, add the geo with points. However I like, just add to that existing plot and get some points on side. That could, of course, also be in Loom. Because it's coming across as a pix map, it's coming in as a raster image, so I have to layer it in this way. And unfortunately in Loom, that works fine, except as soon as you start panning and zooming, there has to be some rescaling of that image, which is a little work, and so it can be kind of slow. That's it. There are many other packages that you'll find very handy to produce maps in R, and I encourage you just to search around for where you might get maps and how you might add them in R.